Hello, everyone. In today's QTFMS seminar, we are honored to host Dieter Lüst from Max Planck Institute for Physics in Munich. And he is going to talk about the quantum gravity and the swampland. So, Dieter, whenever you're ready. Thank you.
So I hope you can see that now. So, okay, yes, thank you very much for the kind invitation for this QTFMS seminar, which I'm very glad to give. So thank you very much, Ada, and also thank you for joining. Actually, I wasn't pretty sure what kind of seminar it is. Therefore, I decided to give a rather general seminar introducing quantum gravity and string theory, because I assume that it's maybe not familiar to everybody, and there are also many young students. So I will do this in the first part of my talk, and then I will proceed and go to the swampland and tell you also a bit more about our actual research right now. So here's a short outline of my talk. I will first recall why we are interested in quantum gravity at all, so the quest for quantum gravity. And then I like to argue that string theory is a very good candidate for quantum gravity. As I said, that is the more general part of my talk. And then in the third part, I come to Swampland and the so-called dark relations. Since quantum gravity, string theory, and also nowadays the swampland is a subject where many people are working on. So I cannot give credit to all people. So what I'm saying today is really based on many papers in the string literature. However, I can recommend you one particular review I wrote with Louis Ankodocki and Ignatius Antoniadis in the year 24. You can see my collaborators here. And later on, the work which I will also tell you about is also largely in collaboration with Louis and Ignatius. So let me start very general. If you look at the history of physics, the history of theoretical physics, new developments very often started by observing tensions between different theories. So at the beginning of the last century, or even at the end of the 19th century, there was a tension between electromagnetism and classical mechanics. And this was resolved by introducing the concept or the observation that the speed of light is finite. And this has then led to the discovery of special and general relativity. Then, more at the beginning of the last century, there was a tension between classical mechanics and the observations that atoms are stable. And this problem was solved famously by quantum mechanics, and it led to a new constant of nature, which was already introduced before, Planck's constant h bar. And now we are basically in a situation where we have Einstein gravity on the one hand, on quantum mechanics on the other hand, and still there's a tension between those. And to resolve these tensions, we need the theory of quantum gravity. And again, the Newton's constant is playing an important role when we combine Einstein gravity and quantum mechanics. The solutions of those puzzles also led always to new discoveries. The discovery related to special relativity is time dilatation. Here we learned that there are matter waves and entanglement. And what we will learn from quantum gravity, most likely, in my opinion, is that they are extended objects, namely strings, and these also go along with extra dimensions, which will also play a role later on in the talk. You might ask, do we need at all a theory of quantum gravity, or is this just an academic exercise? Here, I think the answer is clearly no, because there are definitely situations in physics where both quantum mechanics and general relativity are relevant at the same time. And this is first at a microscopic scale, where Einstein's theory, if you use standard methods of, say, quantum field theory, fails to comply with the quantum rules that govern subatomic particles. However, to describe the physics at the Big Bang and also the quantum structure of space-time, we need the quantization of gravity. But also on the macroscopic scale, we know that we need quantum gravity because we know that there are black holes, and black holes also pose conceptual, very deep conceptual problems. They are threatening the foundations of quantum mechanics, and the keyword is here loss of information, namely apparently black holes violate when they decay via Hawking radiation the rules of quantum field theory. So it is clear that we need a consistent theory of quantum gravity which solves these kind of deep problems. Actually, I just want to remind you that black holes are really known to exist, and the Nobel Prize in 2022 was given for the discovery of black holes to namely to two experimental physicists, Andrea Ghez and Reinhard Genzel, but also to Roger Penrose, who was formulating deep theorems about black holes, and and showed that black holes also, or black hole singularities, inevitably have to exist in general relativity. So to summarize this, there are two kinds of problems in quantum gravity. Namely, first of all, if you use standard methods of quantizing gravity, you will face the problem of singularities and infinities at the Planck length. And this is a question of renormalizability of quantum gravity. But there are also, there's also puzzling physics around the horizon of black holes. And this is connected with the unitarity of the Hawking radiation. So how would you describe quantum gravity? Quantum gravity is the quantization of Einstein gravity, and this implies also that space-time itself should be quantized. So space-time undergoes quantum fluctuations, as it is tried to depict here in this picture. And as we will now recall or argue, is that string theory is indeed so far the best UE candidate known for a solution which is called quantum gravity. Before we come to string theory, let me just show you this kind of famous cube where we depict on each of the sides the three constants of nature which are relevant: the speed of light or its inverse, h bar, and Newton's constant. And turning on one or more of these constants of nature, we are entering some particular regime. For example, if we turn on 1 over c, so making the speed of light finite, we get special relativity. If we turn on h bar, we get quantum mechanics. We can also look at relativistic quantum mechanics, so having 1 over c and h bar non-zero. This is the regime of quantum field theory. But the deep question is, what is happening if we also include Newton's constant? Then we are in the interior of the cube, and this is the regime of quantum gravity or string theory. Actually, one can do a very simple exercise, as Planck was already doing more than 100 years ago. You can combine these three constants, h bar, c, and gn, into one-dimensional quantity, the so-called Planck mass. In this way, the number which comes out is 10 to 19 GeV, a very big number for particle physics standards, or its inverse, basically the Planck mass, square root of h bar gn over c cube, is a very short length scale, 10 to minus 35 meters. And it is precisely at those high energies, or those very short distances, which describe also the physics of the Big Bang, where quantum gravity effects will become really relevant. However, we will also see that the fundamental scale of quantum gravity can be much lower in special circumstances that I will discuss. So there are also situations where the scale of quantum gravity is not 10 to 19 GeV, however lower or even parametrically lower, or where the length scale of quantum gravity, the Planck length, is replaced by some other longer length scale. And this is, of course, very important also for possible future experiments that try to explore quantum gravity. Okay, so now let me come to string theory as a candidate for quantum gravity. And here are the three, or one of the three leading founders of string theory, Green, Schwartz, and Witten, who have also written a beautiful textbook on string theory. And as it turns out, in string theory, quantum gravity and also the gauge interactions that elementary particles undergo arise not as an input, but rather as a consequence of the string interactions. So I think you have heard about string theory, so I will not give you a very elaborate introduction into string theory. It is a theory of one-dimensional extended objects, and we can have two types of strings: the closed strings, which have the form of a loop, and the open strings, which is a line with two ends. And then you can also draw these so-called worldsheet diagrams. When a closed string is starting to propagate in space-time, it sweeps out a two-dimensional surface which has a form of a cylinder, or for an open string, the corresponding worldsheet is a bounded surface. It's a kind of sheet. And that is one property, one basic property of string theory. The second property is that a string can vibrate. So it's really a dynamical object, as you can see in the picture here in the right corner. Therefore, like an harmonic oscillator, there are infinitely many massive, heavy string excitations. And to each of these string excitations of increasing masses, we can associate, if you wish, an elementary particle in the so-called effective theory. So at first instance, we expect that the string excitations have all masses of the order of Planck mass, if the Planck mass is the typical scale of string theory also, or of quantum gravity. And if this is the case, they would be indeed very hard to produce and to detect in collider experiments. And this is presumably also one very reason why the stringy nature of elementary particles was not really seen. However, as I said 1 minute ago, it could be that the fundamental scale, or the typical scale of quantum gravity, is also lower than the Planck mass. And this would also give us some hope or rationale to see even string excitations in Earth-built collider-like experiments. There's always one particular string state, one particular string excitation. It is the lowest string excitation. And one can show that this is a particle that has spin 2. And as it was shown by John Schwartz and Scherk in particular, one can associate this particle with the mediator of gravitational interactions. Therefore, it is called the spin 2 graviton. And this is generic in all string theory. So string theory, because of this lowest excitation, this lowest massless excitation, always contains from the very beginning gravity or quantum gravity. And this is also the key for the understanding why string theory provides a consistent framework for quantum gravity. Secondly, or thirdly, also very important, in string theory, as a theory of extended objects, there are no ultraviolet divergences. And this can be understood, at least schematically, if you look at the simple string scattering diagram here at tree level, if you look at the particle interaction, you see that particles interact with world lines, and the interaction points are always singular in space-time. However, strings here, closed strings, interact, that their world shields are interacting. And as you can see, there's no well-defined or even divergent point in space-time associated to the string interaction. And if you analyze this more carefully, if you also look at loop calculations, you will see that there are no UV divergences in string perturbation theory, which is the key for the understanding that string theory solves the problem of non-renormalizability of quantum gravity if you would only apply the techniques of quantum field theory. Okay, that was basically the beginning of string theory. Another important step in 1995 was the discovery by Joe Polchinski, namely that in string theory, there are not only strings, but also higher dimensional objects, the so-called D-branes. D-branes a priori are just hypersurfaces in space-time, but Polchinski discovered that these D-branes are also kind of dynamical in the sense that open strings can end of them. They can also connect different D-branes. So also in this way, D-branes are dynamical, and you can also show that they have a tension, and D-branes therefore play also an important role in string theory. And indeed, the discovery of those D-branes, these hypersurfaces in space-time, has several far-reaching consequences. One of the most important consequences, in particular also for making contact between string theory and particle physics, is that the gauge interactions like electromagnetism and the strong interactions and also the weak interactions, at least in one formulation, arise from open strings on D-branes. So the elementary particles like quarks and leptons, but also the gauge particles like gluons and photons can be all associated to open strings, which live or are stretched between D-branes. And this has also led to a lot of interest and a lot of work on the so-called standard model building from so-called brain world constructions. You can read this also in this review, which I have quoted here. And one talks about so-called quiver diagrams, where we have, say, several stacks of D-branes, for example, a stack of 3 D-branes, which give rise to the strong interactions. And then another stack, as you can see in the left picture, of 2 branes, which give rise to the SU2 weak interactions. And then the quarks and leptons are open strings, which are situated at the intersection point of those D-branes. And you can then try to build models which come quite close to the standard model of particle physics. So this was done basically during the year 2000 or in the following years. And indeed, many models which are close to the standard model of particle physics can be constructed in this way. And one can also compare them with what you expect at the collider, for example, at the Atlas experiment. And this was also done in several papers. So one can say that with this observation, it is a general feature of string theory that it provides a geometrization of particles and their interactions in the form of branes. And also not only for particle physics, there's this geometrization, but also for cosmology. And we will talk a little bit more about cosmology later. But you learn from that geometry and topology plays a very important role also in string theory, and also to make contact with the low energy world. So there is a mathematical field also of geometry and topology, which is very important when you want to describe strings and their connection to particle physics. All right, so this is also meant with this two picture. Here we have the Atlas detector at CERN on the one hand, and I think this is a Planck satellite on the other hand, which is very important for astrophysical observations. The second very important consequence of the discovery of D-brains, which I like to mention at least briefly, was that one can also model black holes via brains. And not only that, you can also compute entropies for black holes in string theory. And you can compute the so-called microscopic entropy for black holes, counting the number of configurations and compare them also with the Bekenstein-Hawking area law. Here the main breakthrough was in 1996 by Strominger and vacua, and they showed on the one hand that black holes can be viewed as bound states of D-brains, again with open strings in between, and then counting all the open string configurations, they could show that the microscopic entropy of those black holes precisely matches the area law, that the entropy is given by the area of the event horizon of the black holes, which are constructed in such a way. Finally, and maybe this is perhaps even the most famous application or consequence of D-brains, namely holography and the ADS CFT correspondence. And here it turned out that a gravitational system in some particular space, in a so-called anti-de Sitter space, a gravitational background with negative curvature, can be described by a dual quantum field theory on the boundary of the space. And the connection to string theory is that the boundary of the space is given precisely by the D-brane, and the gravitational background, the ADS space, is given by the gravitational back reaction such a D-brane has to space-time. And this was famously seen by Maldacena in the year 1997. And I think the paper by Maldacena is one of the papers, or perhaps the paper, which has the most citations in all theoretical physics papers. So it has really had really a lot of impact. And it also had impact for black holes, because the conformal field theory, the field theory on the boundary of the gravitational space, has to be unitary. And this therefore implies that also on the gravity dual and the gravity part, unitarity has to be preserved. And by this very general argument, one can already say that there cannot be any loss of information in any quantum gravity theory. And because of this, in 2004, Hawking finally declared that black holes behave unitary. One can also formulate it the way that black holes do have some hair, without explaining black hole hair here in this talk. And this was then also admitted by Hawking. This is the loss of the famous bet between Hawking and Thorne on the one hand, and John Preskill on the other hand. And Preskill was arguing that there is no loss of information. And I think Stephen Hawking finally also agreed with that. Also, the real deep, I would say, macroscopic understanding how this loss of information is resolved. This is still a very active field of research, and I think many of the details of this, how black holes get unitarized, is not completely well understood. Finally, also with the advent of D-brains, but also even before, it became clear that there exists a huge space of string vacua. We observed this already with Wolfgang Lerche and Adrian Schelikens in the year 1986. There's not only one particular solution of string theory, and there's not only one particular ground state of string theory, but there are many so-called string vacua. And this I'd like to elaborate a little bit further on. This has to do with the so-called compactification process, but also with the introduction of deep rates. So to understand this, let us start again with the basics of string theory, namely by observing that string theory is only consistent in a particular critical space-time dimension, which turns out to be 10. So one time dimension and 9 spatial dimensions, 10 space-time dimensions. And in fact, in 10 dimensions, string theory basically is almost a unique framework for quantum gravity. However, we have to also then ask the questions, why do we observe only 4 space-time dimensions at low energies in our world? This question is answered by the so-called compactification picture. Namely, the picture is as follows, that from these 10 space-time dimensions, 6 spatial dimensions are compactified. They are rolled on a small, compact 6-dimensional space, which has a particular shape, a particular geometry, and also particular geometry. One can use this picture of a person who goes on a rope, which is in itself not so easy. I couldn't do it. In any case, the rope, the dimension of the rope would correspond to the 4 space-time dimensions, and that is the only relevant dimension for this person. But if you look more closely, the rope also has a finite diameter, and this finite diameter corresponds to the extra compact dimensions. And actually, if one has enough resolution, as for example these little arms have, you could even travel, you could even walk along the perpendicular dimensions and try to explore them and try to see what kind of shape they have. This picture is admittedly rather heuristic, but I think it reflects the real situation also in a good way. What one has in reality, one has a 10-dimensional space-time. It is assumed to build basically a product between 4-dimensional flat space R3,1 times a 6-dimensional compact manifold denoted by M6. And this 6-dimensional compact manifold is also characterized, say, by certain parameters, which we will come back later. It has, for example, a particular volume, a particular size, and these parameters will also play an important role in the effective field theory of which is effective field theory on R3,1. That is one.
Sorry, Peter, can I ask something?
Yes, sure.
When you say 10 dimensions, what string theory basically says is the total central charge of the theory, right? It's not actually the dimension, but the total central charge. And when we try to understand this through geometry, we basically take a 4-dimensional theory and a compact 6-dimensional theory, whereas we can also use non-geometric theories to construct the plot.
I mean, in the usual sense, these are really 10 space-time dimensions. And if you ask me the technical question about the conformal, about the central charge of the corresponding conformal field theory, it is actually not 10, but it is 15, because we have the bosonic coordinates and also the fermionic coordinates on the worksheet. But it is indeed more abstractly, it can be described by a conformal field theory of particular with a particular central charge, in this case 15.
Okay, thank you, thanks.
Then one more question by Omar.
Yes, I have a question. Good morning to everyone. So my question is, what type of signature has this MC manifold? It is pure space, or it has time, or what is this type?
Very good question. I mean, it is pure space. So if you wish, if R 3,1 has signature minus plus plus plus, the signature of M6 is only plus, so it's a Euclidean space. Of course, you could also fantasize that you introduce not only that you introduce also additional time directions, as people have tried, but then you will run into several problems, and therefore normally it is assumed that M6 is a Euclidean manifold with positive, say, with positive signature.
Okay, thanks so much.
In its all directions.
Thanks.
Okay, so that is compactification. Compactification can be also combined with the so-called brain worlds. These brain worlds then bring back the D-branes, which I have introduced before. Namely, instead, in addition to the compact spaces, one can also introduce D-branes, where the gauge and the matter fields are open strings that live on the lower dimensional branes. And these D-branes then, for example, they can fill all R3,1, and they can be wrapped around M6 or can wrapped around certain submanifolds in M6, and therefore there's a lot of ways also to introduce branes. And the proliferation now of the number of ground states comes on the one hand from the observation that the space M6 is by far not unique. This is called a Calabi-Yau space, and there exist many of them. Also, their number is assumed to be finite. And also, there are many possibilities to introduce branes in these internal geometries. Still, it is believed that the number is finite. So what one gets is a huge zoo of compactifications. And this obviously also causes some problems to make contact with reality because of these many a priori many possibilities. And this is a so-called string landscape problem, which says that string theory or M theory is the strongly coupled version of string theory in 11 dimensions, is almost unique. But when you go down to lower dimensions, if you perform compactification, there exists a huge number of lower dimensional ground states, and one can start to count them, and one can apply certain consistency conditions. One sees indeed that there's a vast landscape of presumably discrete string vacua, numbers of 10 to 500 or 10 to 1,500 are often quoted in the literature, and that was found or was a big problem at the beginning of the year 2000 and later on. As I said before, we also observed that there is a big number of ground states already some years ago. And this is a string landscape problem. And it says also if the theory possesses more than one solution, say ground state, one has to assume that each solution in principle exists. So if you wish, each solution can be viewed at its own universe. It has its own elementary particles like quark and leptons. So in other words, one can say that different universes appear as different phases of an extremely complex, perhaps even chaotic system. But it really opens the problem of many possibilities for different particle physics models, and also many possibilities for different cosmological models. And you can even ask the question, as we also did some time ago, what is the probability to find the standard model of particle physics in a certain data set of string compactifications? Not the most general data set, but some particular data set. And what we got that at least there, the likelihood, the chance to find the standard model is about one in a billion. And this is also the reason why nowadays people use, for example, machine or in particular machine learning or AI techniques to explore this string landscape and to see which corner of the landscape or which kind of solutions for which part of the solution one can make contact with the standard model of particle physics. But in general, this is a problem of calculability and also predictability in the landscape. And it also has given rise to the notion of the so-called multiverse, the multiverse picture, which was, I think, introduced by Linde in 1986. And the multiverse picture is also augmented with that you can compute transition amplitudes between the different vacua. One can try to write down a so-called wave function of the universe of the form of Hartle and Hawking. And then one gets a picture of the eternal self-producing universe by Linde. And then also, as it was particular advocated by Susskind, one can also use the anthropic principle, which really simply says that our universe is by no means special, but the observed parameters take their observed values for the simple reason that they allow for intelligent life. And this is one way to single out our universe from those many vacua we have to deal with in string theory. For example, I give you just a short list of so-called anthropic parameters. Very simply, the distance between the Earth and the Sun is, if you wish, already anthropic because it has to be fine-tuned to allow for life on Earth. But more relevant for the early universe, the fine structure and the strong coupling constant, they have to be fine-tuned, and this is important for nucleosynthesis. Also the so-called cosmological constant, which I will mention later on, which is a very important constant, needs to be fine-tuned, and it has a very tiny value, 10 to the minus 120 in Planck units. So Weinberg was arguing that one needs at least 10 to 120 vacua to predict or a way to apply the anthropic principle to the cosmological constant. And I think already years ago, Ehrenfest has argued that the number of spatial dimensions is also an anthropic quantity, because if you think about it more carefully, only with 3 space dimensions, life in the form as we know it is possible. And this is also an argument why compactification has to take place. So this is the anthropic principle, which was kind of popular some 20 years ago, but of course the anthropic principle also created a lot of resistance, because it does not really explain what we see in experiment. So there was really a heavy debate. There are famous scientists like Steven Weinberg who really thought very highly about the anthropic principle. So I do not read you these quotes, but he was talking about turning point and a radical change, what we accept for a legitimate foundation for physical theory. Also in cosmology, the anthropic principle was very popular, as formulated here by a very famous cosmology, Lord Rees. But on the other hand, many people were really very much against the anthropic principle. And for example, David Gross, in his way he put it shortly, the landscape idea, question mark, I hate it. Never give up. And he meant never give up by looking really for an understanding why we observe what we see, not putting it or not blaming anthropic principle. Also, Murray Gell-Mann was saying once, if we really live in a multiverse, physics will have been reduced in environmental science like botany. I think it did not meant it badly for botany, but I think he also did not like the anthropic principle. So with that, I like now, so it's also, I think for you maybe also still to decide whether you find the anthropic principle attractive or not. I think it is still, at least for me, an important issue. But nevertheless, during the recent years, during the recent 10 or 15 years, there was a new development, the so-called Swampland. And I think this Swampland development, which I will introduce now, has put certain aspects of the landscape and therefore also of the anthropic principle in a kind of a new perspective, which I think is very interesting and which I find also very attractive. So as we discussed around 2010, it was believed that we do not have really many concrete fundamental predictions from quantum gravity or string theory. If you wish, it was said anything goes, or some people polemically even said string theory not even wrong, as in this book by Peter Voigt, which I also do not agree with actually. But this was really, if you wish, also a problem for the field. But I think with the Swampland, the paradigm again has changed in a particular way. So since about 10 years, indeed, I think there is a change of the paradigm, and now it is understood that, or it is seen that quantum gravity and string theory can indeed make some concrete predictions of what kind I will discuss now in the following. But the basic observation here is simply said, namely, it is understood and it was clearly realized that not anything that is possible in quantum field theory is possible in string theory or in quantum gravity. Not anything possible in quantum field theory goes, in contrast to this criticism that anything goes. And actually, if you look at quantum field theory, you immediately see that there's an infinite number of consistent of possible quantum field theory. Let me just take a very simple example. Gauge theory with gauge group SUN. Here in quantum field theory, the rank of the gauge group, the n can take any value. So there are infinitely many possibilities, but this is only a very simple example. But on the other hand, in string theory, we learned that, for example, the rank, I think, of the gauge group has to be bound by some particular number. In the same way that we have many compactifications, but not infinitely many. And as such, it would perhaps not be really a very big breakthrough. But what we also learned better or learned more, that one can understand, at least in some sense, the smallness of some observed numbers at low energies by the structure of quantum gravity at high energies. This is called UV-IR mixing. The UV, the ultraviolet, has an impact, has an influence on low energy physics, on the infrared, or also vice versa. And I think it became now more and more clear that this UV-IR mixing is one of the fundamental principles which also underlies gravity and quantum gravity. So I like to explore this also a little bit more in the following. So that is the basic observation, and the Swampland program now is trying to make this more systematic and explore this in more detail. The Swampland program was initiated by vacua in 2005 and also the paper by Oguri and vacua 1 year later. And it asks the following question, namely, what infrared consistent quantum field theories cannot be embedded into a UV complete quantum gravity theory? I told you before that there's an infinitely large number of consistent quantum field theories. And the question is, where is the demarcation line? Which one cannot be consistently embedded or lifted in quantum gravity? And this question now has led to the notion of the swampland, nicely depicted here in the picture by Eram Palti. So we see here quantum gravity or string theory, also in the UV at high energies. And then if we go down, so we could also write a vertical axis, which is some kind of energy scale as well. If you go down to lower dimensions, if you compactify, we discover the landscape. But the landscape is now surrounded by the so-called swampland. And the swampland are those quantum field theories which look entirely fine. They look entirely consistent. If you apply all criteria a quantum field theory has to satisfy, for example, anomaly freedom, but nevertheless there is a way, a hidden, more secret quantum gravity reason that they cannot originate from string theory, or more generally, they cannot be embedded into quantum gravity. And that is the main idea of the swampland. And what we want to do now in the following, we also, I don't know if you see my cursor, we want to basically also explore the borderline, the demarcation line between the landscape and the swampland, because this gives us also some interesting information about what is possible and what is not possible. And it can even lead to some kind of predictions, as it was realized now during the recent years. Okay, so this demarcation line, or in general, the swampland idea, is formulated normally in the form of so-called swampland conjectures. And these conjectures are mostly about the borderline between the landscape and the swampland. They can be rigorous and also less rigorous. So some of them can be almost proven, perhaps not in the sense of mathematics, but they're really very plausible. Some of them are more speculative. They can be less useful, but they can be also useful in phenomenology. And one of the guiding principles very often are properties of black holes. So they're often motivated from general black hole properties. And this is also nice because we want, in a way, also to get rid of the so-called string lamppost principle. We want to see whether something is really true in general in quantum gravity, or whether we need string theory to understand it. And therefore, black holes are very useful laboratory. But nevertheless, many of these conjectures are successfully tested in string theory, and they are all turn out to be correct. Otherwise, I think we would not talk about them. So string theory is a very good also mathematical laboratory for these swampland conjectures. I will now, I mean, there are several of them, and I cannot present you all of them, but I like to take now at the end of my talk, I like to talk about one particular of them, that is the so-called dark dimension conjecture, because in my opinion, it is well motivated. We can discuss about it and also test it in some sense in string theory, but it is really very useful also in phenomenology. Okay. So this brings me to the last part of my talk. I think I don't have too much time, 10 minutes or maybe a few minutes more. So in the last part of my talk, I like to discuss in more detail the swampland and dark relations. And to start with, I need one particular swampland conjecture, which was already pointed out or formulated by Oguri and Wafa in 2006. This is a so-called distance conjecture. And it states, if we have a parameter space, if we have a compactification, there are certain parameters like the shape or the volume of the compact space. And one can then one deals then with the so-called parameter space. And the distance conjecture quite generally or quite abstractly is saying that at a so-called large distance limit in the parameter space, some new physics is opening up. So if we go at some particular corner in the parameter space, which are infinitely or very far away from generic points in the middle or in the bulk of the parameter space, then some new physics is opening up. So whenever we go in a certain large distance direction, new physics has to show up. Otherwise, quantum gravity would be inconsistent. So you ask, what kind of new physics can that be? And what kind of limits we are thinking about? The limits we are thinking about are mainly weak, or if there's a duality, also strong coupling limits. Also like limits where certain masses become very small. So either we go to weak couplings or to small masses, or other parameters become very small. So these are the interesting physical limits. And on the other hand, what is the kind of new physics? And the new physics is that in this infinite distance limit, some additional states, some additional particles become light. These are the so-called emergence of certain towers. And you have to also, and the statement is that one has to include them in the effective field theory description at some point. Otherwise, the EFT would become inconsistent. So the main message is here: if you go to certain infinite distance limit, one needs new light particles to be included in the effective field theory description. And this principle, this infinite distance conjecture, can be refined. This in terms of the so-called emergent string conjecture by Lielerche and Weigand, namely what kind of towers there can be. And in the emergent string conjecture, it is now argued that there can be in particular two towers of light particles. We call them also species at large distances. Namely, there can be either the so-called Kaluza-Klein particles, namely they correspond to 1 or 2 or 3 large extra dimensions. So your Calabi-Yau space, which to start with exhibits some directions in the parameter space where some spikes become, so it grows in 1 or 2 or in 3 large dimensions. So this is the so-called decompactification limit. And the associated light particles are the Kaluza-Klein, the internal momentum states which are associated to the decompactification. That is the one type of towers, or the other type of towers are the so-called light string excitations. And this is achieved when you go to weak string coupling, because then the associated string scale becomes light without too much further of explanation. But this is very important because this simplifies the picture enormously, knowing that there can be only two relevant limits, namely either decompactification or the so-called tensionless string limit, where one has light string excitations. Knowing that, I have now finally to introduce one more important concept, namely the so-called species scale, namely the fundamental scale of gravity. I told you before that in quantum gravity, we expect that quantum gravity effects become relevant at the Planck scale. However, in these large distance limits where additional particles become light, this is not entirely true anymore. And as Giadvali has pointed out in 2007, gravity effects or quantum gravity effects become relevant at a lower scale. And this lower scale is nowadays called the species scale. And in 4 dimensions, it is given by the Planck scale divided by the square root of the number of species. And the number of species are just the number of light particles below the species scale itself. So it's as depicted in this picture. So the definition of the species scale is a little bit implicit, but one can compute it in this infinite distance limits. So this species scale is indeed the scale that replaces the Planck mass in conventional quantum gravity. And this is very important because in the limit of large distances in parameter space, namely in the limit of small couplings or small masses, we get a large number of those species, a parametrically large number of those species. So in these limits, the species scale can become very small, can approach zero, which means that quantum gravity effects can be visible at lower or even at much lower energies than originally thought in, I would call it conventional quantum gravity. So this is a very important observation which we will now discuss or use in the following. And the small numbers I like to talk about now are the two numbers which set the puzzles in cosmology, namely on the one hand the dark energy, the cosmological constant, and also on the other hand the amount of dark matter in the universe. Both quantities are given, if you measure them in Planck units, by extremely small numbers. The cosmological constant is about 10 to minus 120 times m Planck to the 4. And also the density of dark matter is quite small. In Planck units, it's about 10 to minus 19 Planck masses per cubic meter. That is the amount of dark matter that explains, for example, the motion of the stars of the galaxies as we see them in the universe. So the question now is, what are the possible consequences of the smallness of these numbers in quantum gravity? And perhaps even more, are there hidden so-called dark relations between those numbers? I think in view of time, I will only discuss the cosmological constant, and you can ask me also about dark matter. But let me discuss what the cosmological constant has to do also with the Swampland, in which with the large distance limits and what we possibly can learn from that. Indeed, as I have said already, the explanation of dark energy is one of the biggest puzzles in fundamental physics. It's again depicted here in the so-called energy budget of the universe. You see that if you look at the energy budget, only about 5% is given by ordinary matter, like quark and leptons, and photons and gluons. About a quarter is given by dark matter, but around 68% of the energy budget in the universe is given in form of this cosmological constant, or in some form which is called also quintessence. And this is the one which I'd like to address now in the following. So now let me come back to the distance conjecture, and here to the so-called ADS, or cosmological constant distance conjecture, which we have introduced with Eran Palti and Kumon Wafa some 6 years ago. And what we argued is that in the limit of a small cosmological constant, there is indeed a tower of particles, of light particles, at a typical mass scale m. And you can write this, you can phrase this in terms of this very simple relation, that the mass scale of this tower of particles is a certain power of lambda. And okay, now I have to be honest to you. I have to tell you that this conjecture, therefore it is called also ADS conjecture, was first considered for ADS spaces, for spaces with negative cosmological constant. And there one can also really test it very well in string theory. But the conjecture now is also put forward positive values of lambda, so to the namely what we observe in lambda. So what I like to now in a way assume or pose that there is indeed this distance conjecture that in the limit of a small positive cosmological constant, there's a tower of states whose masses scale or are given in this relation. So of course we have now to determine the allowed values of this power alpha, and again without too much of further explanation, one can limit alpha to be between 1/4 and 1/2. The lower limit comes from considering the so-called Casimir energy of the effective potential, and the upper limit is I think it is a strict bound. It is a bound of that comes from massive higher spin states in the effective field theory, the so-called Higuchi bound, and it tells you that alpha must be smaller than 1/2. So this is a range of a priori the range of allowed values for M. But then if you now go further and compare this also with experiments, and this is a dark dimension scenario which was formulated by Montero, Valenzuela, and Waffa in 2022, one can indeed make three kind of possible predictions. Namely, the first prediction is about the nature of the tower. Namely, one can argue that the nature of the tower has to be given by so-called Kaluza-Klein particles, which means nothing else, that there has to be a large extra dimension. String states, light string states are of these masses would be excluded because they would have been seen in collider experiments. So the only option are Kaluza-Klein towers. So the cosmological constant indeed implies or would imply the existence of at least one large extra dimension. The mass scale of the tower can also be determined. Namely, one is let that alpha is very close or is exactly given by 1/4. And one can also ask how many of those extra dimensions of these large extra dimensions can exist. And the answer is either one large dimension that was as it is formulated in the original paper by Montero, Valenzuela, and Waffa. But we have also pointed out with Ankodocki and Antoniadis that there is also the option in principle, also it's more constrained, of two large extra dimensions. So I said before here that alpha has to be 1/4, and now you can just plug in numbers. You can use the observed value of lambda cc of the cosmological constant, and then you will see that the relevant mass scale of this Kaluza-Klein tower is lambda to the 1/4. This is in the milli-electron volt range, and this corresponds indeed to a radius of a compact dimension of the order of lambda to the -1/4, which is nothing else than a micrometer. So the smallness of the cosmological constant in this way of argumentation implies that there has to be one or two extra dimensions of the size of 1 micrometer. And indeed, 1 micrometer for a particle physicist is really a very big length scale. 1 micrometer is basically the extension of a human hair. So it's something which we know very well also from condensed matter physics. So 1 micrometer is really very large, and you might ask the question why we haven't seen an extra dimension of 1 micrometer, because it is really surprisingly large. And this has to do that only gravity can feel the extra dimension. So before I come to it, I show you this picture. The internal compact space indeed would have the shape of a very long cigar. So 1 extra dimension has a micrometer size, and the other ones are principle or have to be in principle much smaller. And as I have just said, human hair has roughly the size of 40 micrometers. So why we cannot see this? The reason is that only gravity can enter the micrometer dark dimension. The other forces, like the forces of the standard model, are confined to a three-dimensional brain. And now the dark dimension scenario has indeed has found some interest among experimental physicists. So there's a group in Austria who want really to test this, namely they want to test the Newtonian force at a micrometer scale. This is so-called ICELI core team led by Eric Adelberger and Markus Aspelmeier, Armin Shaegi and Pietro Zitto. And they are trying to set up an experiment to see whether there are deviations from the force of gravity from the Newtonian force indeed at the micrometer scale. They do this in a dedicated observatory in Austria. And indeed, I was also visiting the lab. It's very exciting. And Kumon Wafa is also engaged in this experiment. So I think this is indeed a very nice string theory Swampland experiment collaboration. This dark dimension scenario predicts the existence of a large extra dimension. This goes along with a tower of light states. And now I told you a tower of light states implies that the scale of gravity gets reduced. For one micron size large dimension for p equal 1, the species scale would be around 10 to 10 GeV. And this also maybe can be tested in other type of experiments, like for axionic surges. Even more dramatically, for 2 micron size large dimensions for p equal 2, the species scale would be of the order of 10 to 4 GeV, 1 tera electron volt. And this could be possibly even discovered at the next run of the LHC, the so-called high luminosity run of the LHC in Geneva, where this run, I think, should start also in 2 or 3 years. So indeed, there are, as you can see, in this sense, testable experimental predictions. The primary prediction is indeed the existence of the micron scale of the large extra dimension of a micron scale in itself. But there are also other predictions. They have to do with the species scale, and they could also affect. They could also imply very interesting new effects in particle physics kind of experiments. So maybe I end with this remark, which has to be made, namely that the dark dimension scenario is very similar to the original proposed scenario of the large extra dimension by Akani, Hamed, Dimopoulos, and Dwali, already from the year 1998. This is a famous ADD scenario. And indeed, with similar arguments, not addressing the problem of the cosmological constant, however, addressing the so-called electroweak hierarchy problem, ADD were arguing that the standard model has to live on a 1 plus 3 dimensional brane. And indeed, the same should also hold for the dark dimension scenario. Otherwise, we would have already seen the extra dimension. ADD is addressing the electroweak scale of around 1 TeV. And at that time, it was argued that one needs at least 2 large extra dimensions of millimeter size. Millimeter size extra dimensions are now ruled out by gravity experiments. And I think therefore it is very interesting now also to test the idea of the dark dimension, which implies extra dimension, not anymore of millimeter size, however, but for micron size. So I think I'm really running out of time now. So I will skip the part of dark matter, which has to do with primordial black holes. And I now simply like to conclude now. I have discussed that string theory is, at least in my opinion, the unique framework for quantum gravity, at least starting in 10 dimensions. However, still, this makes it also exciting and worth to work on for me, with many aspects being still under discussion. Moreover, the quantum gravity Swampland arguments provide indeed new relations among low energy observables, like in the dark dimension scenario. Here I have also left out various interesting new topics about neutrino masses. There was just a new paper on neutrino masses last week on the archive, about Kaluza-Klein dark matter, about primordial black holes, about cosmology, about axions, and several other topics. So with that, I'd like to thank you for your attention.
Thank you, Dieter, for this very nice talk. Is there any question from the audience? Okay, maybe there's
I have a question. Yeah, it's me again. So my question is, in our previous theories, such as general relativity, when we are describing a black hole, it has present some mathematical problems. Let's say, for example, the metric is not defined in the center and in the event horizon, let's call it. So this is the problem that arises mathematically in general relativity, for example, and in quantum mechanics, the Schrödinger equation, it is not Lorentz invariant. No, this is another problem that arises in the mathematics. So my question is, there is a mathematical problem arising in string theories that it's some that it is not already solved?
I mean, there are certain things you can address. Surely also, I don't know whether I understand your question correctly, but there are certain points, of course, you can also address without string theory. But take, for example, black holes. In black holes, we are also facing the problem of the horizon on the one hand, but not only the horizon is leading to a problem, but also the singularity in the center of the black hole. You were mentioning it. And one also tries to understand, in general, the fate of singularities, of black hole singularities, also in string theory, because at the end of the day, I think the singularities should be resolved, they should go away. And indeed, there are people who are working on the microscopic properties of black holes, also often called the fuzzball picture. And indeed, in these pictures, black holes are not anymore singular objects. Taking into account stringy effects, one can also try to resolve these kind of singularities.
Okay, but I mean the mathematics. It is not something that we need something new in some sense. I don't know if I'm very vague about what I am saying, but we don't need to fix something in string theory, such as the Lorentz invariance in Schrödinger equations.
No, I think it's not the question. I mean, many of the one should not be misunderstood. Many of the concepts of general relativity in quantum mechanics, particular quantum mechanics, are still valid in string theory. So string theory in this sense is not a completely new framework which introduces, for example, new mathematics with respect to quantum mechanics. But we also see that with respect to general relativity, string theory provides additional, if you write down, for example, Einstein action of general relativity, it contains the famous Einstein term. But due to the stringy nature, there are higher order terms in the effective field theory that go with certain powers of the curvature. And they indeed also induce new effects, not necessarily related to completely new mathematics, but indeed due to the stringy nature, there are new effects in the effective field theory.
Okay, thank you so much. Thanks.
Welcome.
There's a question from the chat. I will read it. It asks you about the primordial black holes and how
Yes.
they are related to your talk. I think referring to your paper with Alec Bedroya.
Okay, then let me just maybe go back to my slides just a second. Okay, I should share again. So yes, that is indeed related also to the work which I did with Luis Ankodocki, Ignatius Antonionis, and Alec Bedroya. It has to do with dark matter, and one way to explain dark matter is by primordial black holes. These are black holes that are created shortly after the Big Bang, but have survived until now. They're called primordial black holes. But it turns out that to explain dark matter by primordial black holes with standard four-dimensional black holes is very difficult. And therefore, we have proposed that primordial black holes are in fact higher dimensional. They come from 5 dimensions. And in this way, in the nutshell, so their radius, the Schwarzschild radius of these black holes is smaller than 1 micron. And this changes some of their properties. They are longer lived, and therefore one can indeed, they can be lighter, and therefore one can use them as very nice candidates for dark matter. And this is also what we mean in our paper with Alec Bedroya and Luis Ankodocki, saying that primordial black holes have to be 5-dimensional. Let me see if I have a slide on that. No, I don't have, but it has very interesting consequences also for Hawking radiation. And there were some events recently reported by detectors which see high energetic neutrinos coming from the universe. And one explanation of these high energy neutrinos is indeed that they were emitted from a relatively light primordial black hole. So this, in very short terms, is the story of why primordial black holes are interesting here, because they arise natural in this 5-dimensional dark dimension scenario, and they are smaller than 1 micron, and therefore they can also enter into the 5-dimensional bulk space.
Also, there's a follow-up question on that. Is 5-dimensional primordial black holes a unique prediction by string theory? If so, will its detection help in evidence for the theory?
No, I would not necessarily say it's a unique prediction of string theory. I think it's a prediction of the dark dimension scenario. And yes, so if you wish that the dark dimension scenario is a prediction of string theory or of the Swampland, in this sense, also 5-dimensional primordial black holes are a prediction of that.
Are there any other questions from the audience? Maybe there are people who would like to ask questions after we finish the recording. So I would like to thank Dieter again for this very nice talk.
Thank you very much.
Now we can stop the recording.